about. Section 3 of Chapter 11 is called Contingency Tables. Hey, this is one of those sections where they have a Part 1 and a Part 2, and we're only going to do Part 1. That's plenty in terms of giving you something that I think will be useful to you. There's a lot of words in this slide, more than you want to read, but let me just highlight this one. These are called two-way frequency tables. You find them all over the place. You find them, for example, in that chapter problem. What page is that on? Page 584. The table on page 584 is an example of what is called a two-way frequency table. Because, see, you can find the frequency of lots of different things. You can find the frequency of that Gilbert was working. How many times do we have recorded in the data here that Gilbert was working? Nope, not 74. 257, right? What is 74? That is a frequency. You added the 40 and the 34. That's the number of shifts where there was a death. Now you take a look at the data, right? 74 shifts, there was a death. 40 of those 74 means more than half of the shifts that had a death, Gilbert was working. Now take a look at the figure below. They have this huge bar graph. They're computing there the death rate. Now how do you get a death rate? Well, no, that's not what they did. Right? So here are some numbers. Let's see if I can reconstruct a death rate for you here. Now, what's that? Oh yeah, this is all. It's all here. I'll put it back up here too once I need to. But anyways, I'm looking at the 40, the 217, the 34, and the 1350, right? And I want to see how do I get a death rate. What is a death rate? Well, I guess it's the number of shifts you have. Yeah, the number of deaths you have divided by maybe the total number of shifts, right? So let's try this. Let's take shifts just where Gilbert was not working. So let's take, there were 34 deaths out of, well, I guess I need to add 1350 plus 34, right? So that's the total number of shifts. So there's a death rate, 0.02. And now let's compare that to 40 divided by, and now I'll do 40 plus 217 shifts where Gilbert worked and there wasn't a death. Oh! See, that's what the red bar graph is giving you. It's comparing the 2% death rate when Gilbert's not working there to the 15.5% death rate when he is working there. So what do you think? The reason I ask you is that the prosecution gave this bar graph to the jury. Said, look, what do you think? Yeah. Okay. Remember we had something in the last chapter called correlation? We talked about correlation. There may be a correlation that we can demonstrate between the death rate and whether or not Gilbert is working. But this is not what I would call causation. As a matter of fact, if you read at the bottom, it says George Cobb, who was a leading statistician, he became involved in the case, and he said, all right, you can use this evidence to decide whether or not we should indict him. But when it goes to the actual court case, you can't show this to the jury. Because the average person on the jury is going to think, oh man, this proves, well, it doesn't prove anything. It doesn't prove anything about whether or not he's guilty. It's what they call circumstantial evidence. Okay? Now, if you find that somebody's around every time someone's dying, should you look into whether they're the guilty person? Yeah. You ought to look for more evidence. So that's what they're saying here. We can indict this way, but we shouldn't incriminate this way. Okay? If you want to find whether or not he's guilty, you need other evidence. You guys understand the difference? Okay. So I think that's a cool chapter problem. We'll get into that a little more in a minute. But what are we doing here? We're going to study these tables. We present a method for testing. Oh, here's the claim. That's the big guy. What's the claim here? That the row and column variables are independent. See, that's something we've had all along. We learned about independence a long time ago. Sometimes we need the various populations to be independent. And I think actually we did some tests where the two populations were dependent. The pairs were matched. Right? So, anyways, this is going to be a test to figure out whether or not the rows and columns are independent. Remember here, the rows are Gilbert working or not. And the columns, these are death or not. We want to know, hey, is Gilbert working related to whether or not there's a death? That's what we want to know. Right? So we're going to use a test to figure that out. It says we will use the same method. Now you can X this out. This is part 2. We're not going to do homogeneity. What is it? It's whether we test that the different populations have the same proportion. But I'm going to stay away from that. We don't need that. Okay, so we're only going to do part 1. Basic concepts of the testing for independence. Now, we already talked about this. You have a contingency table or two-way table. The important thing to know is that there are two variables. One you put in the rows and the other you put in the columns. It says contingency tables have at least 2 rows and at least 2 columns. If you just had one row, that's not a contingency table. Okay, or just one column. Now, we want to be able to test independence. So we're going to test the null hypothesis. So what is H0? It's that the rows, I'll put it this way, row variable and column variable are independent. That's H0. H1 is that they're dependent, I guess, or not independent if you want. But I want to go back to, boy, what chapter was it that we first saw that word? I'm sorry, row variable and column variable. Just got my eraser. So, again, what... do you remember when it was that we first encountered the word independent? Back in the beginning. Raise your hand if you have an answer, because people are mumbling, but maybe it's just, that's what we feel like right now. Chapter 4? Chapter 4 was on probability. And I'll tell you back when we cared about whether events were independent or not, it was when we were studying something called the multiplication rule. And I think, hey, we got a final in 2 weeks. I'm going to review this right now. The multiplication rule was used for computing the probability of, do you remember? I'm hearing lots of answers, but not the right one yet. A and B was multiplication. By the way, what was or? Yeah, A or B, that was addition rule. This one is addition. That's good to review, because we're going to need that. Okay, but A and B, that was the multiplication rule. What does it equal? Probability of A times, probability of B given A. And that's where I said, okay, I got to explain what that is. But I think you might remember that we were hoping it was going to say this. Probability of A and B is the probability of A times the probability of B. Wouldn't that be nice? But we said there is a situation where that happens. The only time that happens is if A and B are independent. If you have independent events, then you can just multiply the probabilities. That concept comes back right now. Because if we want these row and column variables to be independent, we should be able to multiply probabilities to figure everything out. So I'll show you how that works. Okay, notation. I don't think we have to write anything down here. Well, okay. Your book uses R and C for rows and columns. To me, that's pretty easy. There are requirements. Hey, these are the same as the section we just did. Okay, cool. There's a null hypothesis and an alternative hypothesis. And I mentioned H0 is that the variables are independent. H1 is that the variables are dependent. Which might not be obvious, because normally the way we figure out H0 is we look for equality, right? So one question you might have now is, well, what is equal? What is equal on these problems? Well, I'll see if I can point that out. Your book doesn't really worry about that, but maybe you are. Hey! We get to use chi-squared again. That's our test statistic. So it's kind of nice to put these two sections together. There's a reason they're lumped into Chapter 11. Okay, and that's part of it. You're going to find that what we do in this chapter, in this section, is very similar to what I just talked about. The one difference is E. How do we calculate E? Well, they say, hey guys, do row total times column total divided by grand total. But again, I think it helps if you understand why you get that. So let me go to the next slide where you'll see the same formula, but explained. So I put this slide here. Now, remember, this is the formula. E equals N times P. Right? In this particular situation, we're going to have a table. We're going to have, for example, in the chapter problem at the beginning, 1, 2, 3, 4 categories, right? Each cell is a category. So think of it that way. So how many cells will you have? Well, in this situation, what do you have? John? 4. What about in general if you have a huge contingency table? How do you figure out how many cells are in it? Length times width, which in our example is number of rows and number of columns. They call it R times C. So your book is going to say, look, K, which is the number of categories, is going to be R times C. Or they might say K equals RC. Okay, number of rows times number of columns. So that'll come back shortly. Now, what is N? They call it the grand total. Because where's the grand total in the chart? It's not there. Right? Now, I could add the columns and get a value here and get another value there. Neither one of those is the grand total either. Where's the grand total going to show up? Over here. See that? If you add up those two rows, or if you add up those two numbers, you'll get the grand total. So that's N. N is the grand total. Now, to get the probability of being in any particular cell, okay, we'll see if this makes sense to you. What you compute is the probability of being in the row times the probability of being in what? In the column. See, that's where independence happens. You can multiply the probability of being in the row, that's like event A, times the probability of being in the column, that's like event B, if we know that the rows and the columns variables are what? Independent. So when we say we're going to test the claim that they're independent, the way we're testing it is we're multiplying and then seeing how it works. Because that'll give me the what I expect. And now I compare that to what I observe. And then from here on out, it's exactly the same as what you did in section 2. It really is. So I'll do an example or two with you. But I think you'll find that if you can follow this, that's it. Oh, and notice to compute these probabilities, it's the total over the grand total. So one of the grand totals cancels out. And that's where this formula comes from. Row total times column total over grand total. This is the E equals NP formula. It's just that we canceled out one of the grand totals. Because grand total was N. No, I didn't. So before the example. Well, okay, you knew number 2 already. Tests of independence are always right-tailed. Why? What kind of test statistic are we using? Chi-squared. Okay, so we knew that. But number 1 you didn't know. How many degrees of freedom do you use? I actually don't understand exactly why this is the case. Because I said that K is R times C, right? Now, normally, when you do a goodness of fit test, back in section 2, we use K minus 1 degrees of freedom, right? But what they say to do here is use R minus 1 times C minus 1. 1 less than the number of rows. Multiply that by 1 less than the number of columns. That's not K minus 1. For example, in the chapter problem, here's what we have. We have a picture of, right? This is the Gilbert thing. It's a 2 by 2, right? So there are 4 categories. K is 4. But how many degrees of freedom would you use? 1, because you're going to do 2 minus 1 times 2 minus 1. That's only 1. See that? So it's something about the tables being linked up the way they are that you lose degrees of freedom. Not that I've been real precise with you about what degrees of freedom are anyways. But anyways, this is a question I have for myself. All right. But anyways, that's what you use. R minus 1 times C minus 1. P-values, computer software. I'll show you how to do that. Okay. Test of independence. Yeah, I think I said this, right? Cannot be used to establish cause and effect. All it does, if we have dependence, that means there is a relationship between the two variables. So there's a relationship maybe between Gilbert and the deaths. But we can't say that he caused the deaths. Matter of fact, maybe his boss made sure he was always there anytime there was a murder. Well, I'm not going. I don't know the facts of the case. But I'm just saying, there's other explanations. All right. What are we doing here in this example? Table 11.6. Let's see if I can find a page number for you. So, anyways, you can see there's the result from the experiment for this disease that, we want to see how this treatment works. Okay? So you can either use 20% extract or 60% extract. Now, what does it say? It says the first cell lies in the first row with a total frequency of 178 and the first column. What they're doing here is just saying, hey guys, do you know how to find what we call the expected frequency for the first cell? Okay, so let's see. It's 88, but now what you want these totals. So this total, the first row, if you add those three up, you get 178. If you add these two together, you get 103. The grand total will be the sum of all frequencies in the table. So let's see, I have 52 here. I have 52 here. So I take an extra 104 and 103, so the grand total is 207. And I guess if I added these up, that'd be 29. So if I did 178 plus 29, that's 207. Okay? So that's how you deal with the table. That 207 is what's going to be my grand total. Okay? And so, when you go to compute E for any one of the cells, that 207 is in the bottom. Now notice, to get it, we did row total times column total over 207. That was a real fast way to do this. That's right. So actually, let's do a different one. Here, let's go back to the table and do. Okay. So we just computed. Matter of fact, let me write it down. We just computed that the expected value for the first cell was 88.57. Okay. Hey, that's pretty close, isn't it? That's expected. So now you were saying, let's suppose we're in the second column. Shall we? All right.
Just so I knew.
Yeah, let's look at that. Let's look at that. So what's expected here? Well, okay, it's going to be something over 207 because that's the grand total. So what would it be in the numerator? I guess it'd be 52 because that's the number that we're in this column times what? Oh, you want me to go down there? Okay. So 52 times 29 over 207, that's what we expect where the 4 is. So I need my calculator out to get that. Pardon the mess, I'll clean it up in a minute. 52 times 29 divided by 207, says that, okay, I expect 7.285 there. So I didn't get as many as I'd expect. But that's okay, right? You could have a little bit of deviation. You guys follow that? No. Kate, question. Okay, let me go back to the 207. So that's what's called the grand total. Is 155. And then there's another 52 here, because there's 3 columns in this particular example. So I added 103, 52, and 52, because those are the sum of each column. You could do that too. 178 when I add across, 29 when I add across, and that's 207. You can get it either way. No, not extra numbers, because I'm going to need those numbers later. And that's what I'm showing you right now. When you go to compute E for this cell, you need to do 52, because it's in column 2, times 29, because it's in row 2, and then divide by the grand total. Yeah, K is 6 in this one. That's right. Okay? So you really do need to know those totals. And actually, you know, it's kind of funny, because I remember earlier in the year we had tables like this, and they always tallied it for you. But here they're not. I guess they want us to tally it. Okay. Yeah, so how did we get 88.57? We do 103, because that's the total of the column, times 178, and put that over 207. Guys follow that? So we can compute expected for every one of these cells. We'll have 6 expected frequencies, and we are given 6 observed frequencies. So let's see what goes next. Okay, common colds are typically caused by a rhinovirus. Great. Blah, 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 blah. Because I don't read any of that. At that point, I say forget it. It's too long. I look for what word? Claim. Ah, test the claim. Now I start zoning in, because that's important. Test the claim. What's the claim here? That getting an infection or a cold is independent of the treatment group. Claim. Getting a cold independent of the treatment group. By the way, in that chart, getting a cold, is that the rows or the columns? Wasn't that the rows? The rows said infected or not infected, right? See that? Hey, you got a cold or you didn't get a cold? The columns, what's this mean? Placebo? Yeah, you give them medicine, right? It could be a sugar pill. It's a pill with no medicine in it, right? And for years, people have done this placebo. I saw just recently there's a major test out that says the quote, placebo effect. See, when people think they're getting treated, sometimes their body responds better. I saw just recently a statistical study that indicates that maybe that's not true anymore. Maybe we were wrong about the placebo effect. So I'd be curious to know what people find out about that. But anyways, here's 2 different treatments, right? So they're going to compare the placebo to these 2 different treatments. This is very common practice in medicine. Okay. So we want to say, hey, by the way, what would that mean? If getting a cold, if your chances of getting a cold are independent of which group you were in, then what would that tell you? Well, kind of. It doesn't tell you anything about the doctor, but it does tell you something about the medicine. Right? If the medicine has no effect, If it's right? If getting a cold is independent of whether or not you're on the medicine, then maybe we should look for a different medicine. Right? That's kind of the idea. That's what this says. What does the result indicate about the effectiveness of this as a treatment for colds? What's that? Yeah, it might say that. If we find out that they're independent. Now we'll see. Are the requirements satisfied? Randomly assigned to treatment groups, frequency counts, expected frequencies are all at least 5. Oh, wait a minute. What about this guy? Oh, but he's what kind of frequency? Is that expected or observed? That 4. That's observed. Remember what the expected was? It was 7 point something. I checked that already. Remember that? So that's okay. We need everything to be at least 5 for the expected. Okay. They computed all 6 of them. All 6 E's. They subtracted. They did it. They got chi-squared, and they say it's that. Yeah, that's fine and dandy. How the heck did they get that? Well, I'll show you. I'll show you how to use technology to do it. Right? But they say they did it. Now, supposing they did it. They got chi-squared. Next, we want the critical value. How do we get critical value of 5.991? Well, they say, look, we know alpha is 0.05. And they say, okay, number of degrees of freedom, do R minus 1 times C minus 1. That's going to be 2. So if you look up on that chart, degrees of freedom is 2. Alpha 0.05, you'll find that this is your critical value. So what do you think? Do we reject the null hypothesis or fail to reject? Fail to reject, right? We're not far enough. Here's 5.991. That's the critical region. But the test statistic is only 2.9. So we fail to reject the null hypothesis. The null hypothesis said that they're independent. Hey, so maybe we're in luck. Maybe this medicine does work okay. All right, let's see. Yep, that's what I just showed you. Let's see. We fail to reject the null hypothesis of independence between getting an infection and treatment. Yeah, good question. Hold on a second. Did we prove that they are independent? No, we failed to reject that they are independent. Okay, so we didn't prove it. But it appears that getting an infection is independent of the treatment group. We haven't been able to reject it yet. And so if it is independent, that wouldn't be good. Okay? If you want to demonstrate that a drug works, you want to reject this claim. You want to say, look, these aren't independent. You could see that it works. That's kind of the idea. You guys follow? We are tired. Get that look back again. All right. This is the same thing we saw in the last section. I'll skip that. Okay. So yeah, I thought I might finish with the chapter problem. Do you want to go back to it? Then we'll close up shop. I think that's the plan. So on page 602, they do the chapter problem. And it says, okay, we had that table. Test the claim that whether Gilbert was on duty for a shift is independent of whether a patient died during the shift. Because this is such a serious analysis, use a significance level of 0.01. All right? We want to really be sure here. What does the result suggest about the charge that Gilbert killed the patients? Now, what do? They give us the expected frequencies. They went ahead and computed those. We have the observed frequencies in that table. And they're showing you here how to use Minitab to do this. So maybe what would be good is if I show you how to use the graphing calculator to do this. How about we do that? Okay? And I think that'll end class then. All right. So here we go. We're going to enter the table as a matrix. The table at the beginning of the chapter, I'm going to show you how to enter it as a matrix. Okay? Now, you need to press the matrix button on your calculator. And for me, some of you just have a button that says matrix. For me, I have to go above the x-1 key. I have to hit second and then hit that x-1, and it takes me to the matrix menu. And actually, I have some different matrices on here already. Okay? I'll show you one of them. Here's, if I just press enter right now, it'll say, hey, do you want to see matrix A? And I say, yeah. And it shows me a box full of numbers. Right? Now, this was something I did with my finite math class today. But for you guys, we want to actually take the table that's in the beginning of the chapter problem, and then we want to, put that in. All right, so let's do that. We want a 2x2 matrix. Yeah, so the way you do this is you hit second matrix, go to the right to edit one of your matrices. I guess I'll put mine in for F, because I don't have anything for F yet. So I'll press enter. And the first thing it says is, how many rows do you want? I want 2 rows. As soon as I do that, see there's an extra row now. Then it says, how many columns do you want? What do we want? 2. And we want 2?
Are you doing table 11.6?
No, I'm doing the very beginning of the chapter problem. I thought we'd see if Gilbert is a serial killer or not. All right, here we go. So there were 40 shifts with a death when she was working. There were 217 shifts without a death when she was working. Now, when she wasn't working, we had 34 deaths, and we had 1,350 shifts where there was no death. So there's my data. That's right from the chapter problem at the beginning. Okay? All right, so I'm ready. I'm finished. I'm going to press the stat button. Okay? I'm going to go over to tests. And we're looking for a chi-squared test. So I have Z, T. I learned how to do those. These 2 sample I never touched yet. I don't think we will. We're looking for a chi-squared test. There we go. For me, it's choice C. It's above the linear regression t-test a couple tests. Okay? By the way, this ANOVA, this is the thing I thought I'd finish the course with, chapter 12. But you guys were kind of down on that, so we'll see. Okay. Oh, it says, hey, where are your observed frequencies and where are your expected frequencies? Oh, I only put in what so far? Observed. All right, I got to quit. We got to put in the expected. So we'll go back and do that. Question, David. Let me show you how to fix it. If you go back, you press the matrix again. So second matrix, right? And you want to fix something. So like if I want to fix something, I would go over to the right to edit, and then go down to F, okay? And then using the arrow keys, you can move wherever you need to and just type it over. Yeah. Oh, okay. Then you can go on top of A and just go on top of these numbers and type them over. Okay? We're going to do chi-squared, but you can't find it yet. Don't worry yet because I'm not ready yet. There's something else I still need to do. Yes? That's what I'm trying to explain. Oh, cool. Oh, thank you for reading that. Save us a lot of work. All right, so I think we are ready if we have it in there. So let's do this. Let's hit, we're going to hit the stat key. And Annette, you asked me which test. Let's go to the right. Okay. So I'm at the test, and I'm going to go up because I'll get there faster. I want to get to chi-square test. Did you find it? Yeah, go up. Hit the up arrow. I'll pause this. Here we go. Okay. So thanks to Kate being so astute, all we have to do is tell it the observed. Now for me, that's matrix F. That's where I put it. F. And then the expected, where do you want to put that? This is going to put the expected frequency somewhere. I'm going to go ahead and put them in G. So they're kind of next to each other. You could do A and B, sure. I'm going to go ahead and calculate when I'm ready. It'll also draw me a picture, I guess. Well, maybe I'll try that next. But let's calculate. Whoa! So what did it do? It got a chi-squared value of 86.48. It tells me the p-value. Oh. How do you read that p-value?
Well, it's so small.
Incredibly small. E to the negative 1 times 10 to the negative 20th? That's a seal number that's so small. Right? Yeah. Because if you actually read it, it's .0000000. Well, 20 of those, right? Well, 19 of those and then a 1. And then DF, what's DF stand for? Did it do that right? Yeah, because 2 minus 1 is 1, so 1 times 1 is 1. All right, so we have a really small p-value. That's way smaller than the .01. So we go ahead and reject the null hypothesis. So what was the null hypothesis? Reject independence. So what does that mean? Yes. There is a what? Relationship. That's the right word. We can't say that he caused the death or she caused the deaths. But we could say that there is a relationship between, so this, and maybe what I should say is, this suggests there is a relationship between Gilbert working and the deaths. And deaths occurring. I can't say lots. I can just say there's a relationship.
You can't say lots.
No. I mean, it's either deaths occurring or not occurring. What, right? There's a relationship between. Okay. Yeah, I guess it's time to go. The thing that'd be interesting for you to do probably is to go ahead and look at the expected frequencies and see that it calculated them nicely. Okay. Well, we're out of here. If you guys have homework to turn in, I could take that also. And I'll see you.
Just go back and look at my
Have a happy Thanksgiving, everybody. Okay? Have a happy Thanksgiving.
we then just go back and look at
Yeah,
me.
I'm going to do that now. Yeah, I'm going to do that now. No, we did. There was one small assignment. You could do it for next week if you don't have it for today. That's fine.
I still can't get it to delete.
What's that?
I still can't get it to delete. See, I have this problem. I can't delete
Okay, well,
anything.
go over to edit. Now press enter. Okay, now you can change anything you want.
Yeah, but how do you get rid of them?
Oh, you don't want them anymore.
Well, because the problem is has this.
Okay,
I
so
can't
go
get
to
rid of
edit.
it.
Press enter. And, oh, you don't want that? Why?
Well, because then we leave it blank on there.
It doesn't matter.
Oh.
It really doesn't matter.
But if I keep filling in other ones,
That's fine. If you could write over these things. You know what I mean? If later you say I want to use matrix A again, let me make it a 3 by 2 matrix. No, that's 32. That's too big. 3 by 2. And then, I could fill in some numbers. Okay? And then quit. And now it's a...
but it's not going to calculate each time. Like if I fill in all of these, it's not going to calculate all of them. Right.
What do you mean calculate?
Like
When
just-
you go to
just
do the
what-
chi-squared?
Yeah, just what they tell. Just the
When
ones
you go to
say.
right, when you go to do the chi-squared, where is it? Stat, tests, chi-squared test. You tell it which matrices you want to use.
Oh,
Okay?
All right.
That's what I just did.
Okay.
Okay?
All right, thank you.
Sure.
All of my homework from 2019 together.
Cool. Thank you, Sonny.
Thank you. Have a good week.
You too. See you next week.